Howdy, my name is Angelica,
And my name is Quentin.
and today we will be talking about our biosignal, which is spirometry. First, I'm going to give a little background on spirometry in terms of its physiology. Basically, spirometry is a medical test that helps to test how well your lungs work, like how much air you inhale, how much you exhale, and how quickly you exhale. This is typically measured in flow versus volume or volume versus time. This test can be used to diagnose breathing conditions like asthma, chronic obstructive pulmonary disease, or COPD for short, and so on. It can also just be used to periodically check on lung conditions to test whether or not a treatment is effective. A few key measurements that are taken from this are forced vital capacity, or FVC, force expiratory volume, or FEV1, and the ratio of these two quantities, or FEV1 over FVC. FVC is the largest amount of air that you can forcefully exhale after breathing in as deep as you can, while FEV1 is how much air you can force from the lungs in 1 second. Lastly, the FEV1 over FVC ratio is the percentage of the FVC that expires in 1 second. There are various inputs that can influence lung volumes and or capacities. Some general factors are age, height, ethnicity, physical activity, weight, and so on. Some physiological factors that can also influence this are the rate of airflow flow and vital capacity. Additionally, a normal reading of FVC and FEV1 is equal or greater than 80% of a reference value that is used, and a normal reading for the ratio is equal to or greater than 70% of the reference value. Thus, if the results come out to be little lower than those values, then it indicates an abnormal reading, which suggests that the lungs are experiencing restriction in its capacity. Individuals who get such an abnormal reading have an increased chance of having a lung condition or disease. Therefore, there is a need to measure lung capacity accurately and effectively.
The spirometer was invented in the 1940s by an English surgeon, and it consisted of a calibrated bucket that was placed upside down in water and could measure exhaled air from a tube leading into the bucket. The Englishman later coined the exhaled volume of air vital capacity, as this value could be used to predict future health problems and potential premature mortality. From the 1970s onward, spirometer designs moved from water displacement methods to the use of electronic flow. And while mechanical options can be just as, if not more accurate, most spirometers today have to be integrated electronically in order for the data that they record to be acquired and stored automatically for a physician to view and interpret at a later point. And this is where our design comes into play. And seen here is our circuit design broken up into 4 parts. The first part, section A 1.5 volt source is coupled with a force sensitive resistor as represented by RS and V1. And then the resistor has a range of 200 to 100,000 ohms. And this resistor acts as a potentiometer, and when it is set at the halfway resistance point, it can measure the inhalation as well as the exhalation force of breath. The resulting voltage from this section is fed into section B, where it is amplified with a gain of -10, with the input resistance being 200 ohms and the feedback resistance being 2000 ohms, represented by R3 and R4, respectively. And this is for easier visualization of the signal by the physician. The resulting inverted voltage from section B is then sent into section C, which is an inverting active low-pass filter with a cutoff frequency of around 7 Hertz, which is calculated from the 23 microfarad capacitor and 1000 ohm resistor represented by C1 and R6 in this diagram. And this resistor and capacitor combination is to account for the maximum human breath rate of around 196 breaths per minute, which comes up to about 3.2 Hertz, and the loss of data due to sampling rates. This also accounts for the previously inverted signal sent from section B. After this, the signal is output to a microprocessor to calculate the approximate units of measurement and to display to the physician in a nice pretty graph. Section D consists of the power source for the op-amps so that the full range of the signal can be read without any saturation. And it consists of the positive and negative 15-volt sources, represented by V2 and V3.
And here are our references. Therefore, that concludes our presentation. Thank you for watching.